Hello everyone, good afternoon. Welcome to the class ECE317 Digital Signal Processing. Today we will keep working on the sampling process. Okay, this is a ECE317 for the 10th week Wednesday's class. The sampling process. Okay, today we will consider how to restore the original signal based on the samples. Okay, restore. We want to restore the original signal. Okay, and the thing is like that. We start from a continuous time signal, and we suppose this is a band limited signal. Band limited. Then the spectrum looks like this. This is a capital XC of J omega. This is a XS omega, and we have the limited frequency, the highest frequency. This is a omega n, right? Things like that. Okay, then we take samples. For this kind of things, if you want to restore, you need to keep all the information. So you take samples with a step t. So every t you pick a sample from XC of t, and this t you will choose its number smaller than pi over omega n. Okay, this is a Nyquist sampling step. So you need to choose t smaller than this step. Okay, and then you can have the sample date x of n. It is xc of t. Now t is n times capital T. Okay, and in the frequency domain we have these capital X of e to the j omega. It will be 1 over t summation of all those xc for k run from negative to positive infinite, and every k here is omega minus 2k pi. If you put the plus here, there will be same thing, just a reverse order, right? Okay, so you have the in the frequency domain a formula will look like this, and we can see it in a graph. It will be something similar with this, but you need to change the scale. Every 2k pi, every 2 pi, we have a copy. It's a negative 2 pi, right? Things like this. And at this point, now is a omega n times t. Right? You know, omega n times t is smaller than pi, right? This is 2 pi. The middle is pi. Right? Middle point from 0 to 2 pi is pi, and omega nt is smaller than this pi. Then you have a gap between these two peaks, right? This point will be 2 pi minus that omega nt, right? 2 pi is here. This is center. We'll go backward, right? Yeah. Okay, this is a xn. Now how to restore? The thing is that when you look at these spectrum, you look at this in the frequency domain, you see this part contains all the information of this one. So to restore, just you try to find the signal with a spectrum in frequency domain, this one, that will be fine. Okay, then we need to work like this. We define another signal xs of t. Now this is a signal in time domain, it's an analog signal. This is built based on x of n. We have these samples, right, xn. So this one we define it as summation of all these xn times the dirt of t minus n capital T. Right? We define xs of t by this way. The things like, for example, this is a xc. Then we take sample. Then we will have this is t, right? This is 2t. Every t you take a sample, and this will be n. Every n you have a value. So you have this value, this value, this value, this value. And this is n. This 4 value according to these 4. Right? 1, 2, 3, 4. 1, 2, 3, 4. The waveform are similar, but the scale is different. Scale here's every one as a step. This is x of n, and then we have x s of t. This is function of t. It is also some similar with these, but the step go back to time t. Every nt you have a sample, so you have this. This is t. This is 2t. Then you have parse. Right? You have parse like this. This is xs of t. Is dirt unit impulse, right? You have impulse, and the magnitude change, so it looks like this. This is xs of t. Actually, this go to infinite. This will go to infinite because dirt for continuous time signal, dirt will go to infinite. Yeah, it's an impulse, right? Unit impulse, but the value will go to infinite. Its integral is 1. The value will go to infinite. Okay, this is xs. Then for this xs, we have this one. In the frequency domain, it is 1 over t summation of xc of j. Now is omega minus 2k pi over t. K run from negative to positive, infinite. Is this one. And in graph way, you can see here we do not have scale on omega, so the waveform in the frequency domain, in the spectrum, is exactly same with this. So it is same with this. The same. Here's omega n. Here's a negative omega n. But here's a. If here's a, here will be a over t. Right? I have 1 over t in the front, like this. And then we have copies of them. Every 2 pi over t we have a copy. So this is a 2 pi over t, and another is a 4 pi over t. So this side is a negative 2 pi over t. Then we have a copy same with these. Now the waveform of each peak is the same with these. We have this one. All right. This will be 2 pi over t minus omega n, right? And this is the center. Center will be pi over t, right? Here's 2 pi over t. The center will be pi over t, center of this interval. All right. Then we just restore. I use xs of t, go into a field, h of j omega. Then this side is xr of t. Xr of t were equal to the original signal. So by this way we restore it. We start from x of n, then we build xs. Let xs go across this field, we have xr. So we restore it. Alright. And what is h? H of j omega, it will be a rectangle. It looks like, put the graph here, like this. This value will be t, right? T times this 1 over t, a over t, I get a. So we can go back to the original spectrum, right? So here I need a t. This is omega, and this place is this point. So this is a pi over t. This will be negative pi over t. So this is h. H will equal to t or 0. When omega in this period, this is if capital absolute value of capital omega no more than or maybe equal pi over t, and this is the other side, omega larger than pi over t. Right. We have this. Sorry. Okay. So this is h. We restore by this way. All right. Okay. Now we can have the whole process of the sampling for the sampling work, right? We start from this way. We start from xc of t. Then we take sample. We call this as a AD or CD converter. Analog to digital or continuous time to discrete time, CD or AD. Yeah, both name might work like good. And you need a T. T is the step. You will set the step. Every T you will take sample. Then you have xn. Xn is xc of n times t. Right? If you have this one, this is sampling. Sampling. Right. And restore. You have x of n. Then you will have. You still need the same t. You have xs of t. Xs of t, which is a summation of x of n times delta of t minus nt. Okay, I put it here. And then you need that h of j omega. Then you can have xr of t. Okay. If okay, I describe this. This is h. H or looks like this. Here's a pi over t, the capital omega. Here's a t, right? It looks like this. So we have two sides. This side we take sample, and this side we restore. But the restore we need some condition. If xc is band limited, is equal to 0 for omega larger than omega n, and t smaller than pi over omega n. If we have these two conditions, then we say xr of t were exactly same as xc of t. We do the restore successful. We have the original signal. Start from the sample date. By this way, we can have the original signal. XR is just XC. If without these two conditions, we still can work like this. But the result signal will be, you have some errors. You cannot make sure the restored one is just as same as the original one. So I say this is a condition n. Alright, I said n is the Nyquist one, right? This is Nyquist step, Nyquist sampling step, right? T should be smaller than this step. This is condition n. Without condition n, we still have h. We still have all of these. Right? We still can take sample, no matter what is t. Right? You set the t, any t, t might be larger than this Nyquist sample step, but you still can take sample, right? You can take sample, and then you can also do this kind of restore process to have XR of t. However, by this way you can have XR. You cannot make sure, you cannot guarantee they are same. Maybe they have some errors. So you still have all of these, but XR of t cannot equal to XC of t in general. However, you still can discuss something. You can make the maybe they are similar, right? They are approximate. In case you have some small errors, things like that. Yeah. But here I don't discuss that case. I just leave it here. All right. I leave this statement here. Okay. This is what happened in frequency domain. We can also see the same process in time domain. What it is. In time domain, here's xn, right? Xn take sample. Take sample, we have xn. Then xn we have xs. Then we have xr. So this process in the s domain, in the frequency domain. Oh no, I go to frequency domain. Sorry. In frequency domain, we have xs of j omega times h of j omega or equal to xr of j omega. Now we have these. Yeah, suppose these were equal to xc of j omega. Hopefully, if we have that condition, Nyquist condition, if we have this condition, then they are same. Alright, we have this one. Then we go back to time domain. I put this one in the front. Then xr of t were equal to a convolution of xs of t, convolution with that h of t, where h of t is the inverse continuous time Fourier transform, inverse Fourier transform of capital H. It's this H. It's a impulse response actually. This convolution is in the time domain, continuous time. And this one, by some calculation, I don't go over the process. The result will be a summation of, because xs of t. What is xs of t? Xs of t. Yeah. Xs of t. Where it is? Oh, it's here. Sorry. Xs of t is this one. Its value just some x of n, and for the t other than nt, they are zeros, right? So zeros and those x of n. These are the values of xs. Then you apply the convolution here. Finally, you will have a summation. This is just x of n, x of k, I see. Summation for k run from negative to positive infinite. And h, what is h? H will be sinc function. H will be sinc function. Capital H, it is a rectangle. Then we have lowercase h. This is j omega. It's a rectangle. Then h of t will be a sinc function. Sinc function. Sinc, let me see. It will be sinc function. Sinc function. H is here, right? H is here. H is like from pi 0 to pi t. So this one will be sinc of t over t. Over t. Pi over t is a t over t. Yeah. So h of t will be this one. H of t will be this one. And this here is a sinc of, there will be t shifted by because xs is shifted by t. XS is here shifted by NT. So here is also shifted by NT. Is shifted by NT over T. Is this one. So XR we can calculate directly from here's a K. From the time domain will be this one. We have value of the sample value. Every sample times a sync, then do the summation. So the thing is like this. Suppose I have sample value. This is a x of 0. This is a x of 1. This is a x of 2. And here's a t. Here's a 2t. And the sync function is a negative t. Sync function will be a negative t. No one. Will be a thing looks like this. And here will be another one. And here will be another one. Sync function. Sync function. This one will be looks like this. Sync function. Right? And this point, this will be t. 2t. Here will be 1. Like this. And to summation, you will have the curve. So this curve gives us the XR of t, and XR will equal to XC when the condition ends. We have the Nyquist condition, right? Okay. Actually, this part I want to show you this part here. Actually, you need some hardware. You can do this in some different courses. For example, in the communication courses, I think you will have the chance to see these kind of things. You can build a circuit to realize a field like this, and from the sample date, this will be a sequence of parts, right? Sequence of parts depending on the original signal. Then go over a field, you will have the signal looks like this, right? Things like that. You need you can have a signal generator. Then you build a circuit. Then you can have it. But in this course, we can do this part. We can have this part, XR of t. We can calculate by this way. They are same meaning. These two are same meaning. This one, by this way, you can realize it as a kind of a circuit, in an analog way. And this one you can realize it in a calculation way, a computer way, right? Digital way. This one just summation of all of these. Now we can have a look in the MATLAB. Let me go to this is ECE317. Okay. Let me edit. This is for the lecture 10. Wednesday, 10W. Alright, let me edit these. I want a sample signal. I take sample from a continuous time signal and then try to restore it. Okay, what kind of signal can we use? I can use this one. For example, I use right here. Example, I use a XC of t, which is whatever, like a 2 of cosine 10 pi t, and plus 3 of sine of 7 pi t. I consider this signal. This signal, we want to take sample, so you need to know what is the Nyquist sample step. You need to know what is the band limit, frequency limit. So this frequency in omega, you have 10 pi, you have 7 pi. Okay, so yeah, in frequency domain you will have things look like this, right? Two frequency, which 10 pi here's a 2, that one is 3. Then this is omega n. omega n is 10 pi. So use a sample step t or smaller than pi over omega n. That will be 0.1. So we can choose t smaller than 0.1. That will be good. For example, I can use t 0.08. Yeah, you can also use 0.09 or 0.05, whatever smaller than 0.1. That will be good. I use this as a step to take sample. Okay, xn will be xc of nt. Now let's work on it. Firstly, let's see what is xc, right? So I use a t run from, it doesn't matter, 0 to with a step to like 3. Yeah, hopefully it works. I choose a time interval, and in this interval I have xc of t, which is 2 times cosine of 10 pi, 10 times pi times t, and plus I have 3 of sine of 7 times pi times 7 times pi times t. Alright, so this is xc. Firstly, we can have a look of what is xc. Plot t and xc. Alright, this is the first part of our code. We have xc, and we can have a look at it. We can try run it. F5. Yeah, it's running. Oh, I need to save it. Okay, just save it. Run it. I got something wrong. Line 2. Line 2. What is wrong? Index into matrix negative or 0. Oh, sorry, I don't need this. Just xc, yeah. Just xc will be fine. This is a vector. T is inside. Okay. Alright, this is xc. Right? It looks like this. Then we take sample. Take sample. I use capital T is 0.08. I use this as capital T. And then I choose how many samples and run from 0 to how many samples do you want? Like I choose 50 samples. 50 samples will be how many? 50 samples times that 0.08, I have 4. Not too much. Maybe 30 samples. Okay, 30 samples. And then I can plot. I want xn, not plot. Xn is the samples of x from xc. So actually, same with this part. Same with this part, but t, not t. T now is n times capital T. And t times capital N. N times capital T, same thing. N times capital T. I have xn with these. And then let's show them together. So, okay, let's put the plot here. Plot T and xc. Then I have n times T and xn. Xn, I use a circle for it. Okay, let me run it. Alright, here, you see, those circles give us the samples. If we just look at those circles, we just look at those circles and remove these. What will happen? The circles just look like this, right? These are the symbols. These are the symbols. If you just look at symbols, by your eyes, it seems like nothing, right? It's so like a mess. All right. Let's go back. Keep this. Okay. Now I have a signal and I have the symbols. Now I want to restore it. So for that N, I use a capital N. This is capital N and capital N, and capital N is 30. So I can have different. If I want different symbols, I have 30. Right? If you want like 100 symbols, you just change this N to be 100. Right? You can have more symbols. Now I want XR. What is XR? XR is the summation. I go to here. XR is this part. Summation of xk, the symbol value, times the sync function. Okay. So this is a summation of. Okay, I use t's r xr of t, right? So I use the same t. So xr equal to, firstly I just let it equal to t times 0. So that means I have XR is a vector, is a list of values with same size as t, but all the values in XR now are zeros. Then for k run from 0 to capital N. Okay. So for every k I have a symbol. By that symbol I need to add that it is XR plus, let me see, the formula is here, times sync. XR times, okay, it is XR plus the symbol, the XN, the case value of XN. Oh no, this is a XK, so N should be plus 1. This is the index. In the MATLAB, the index starts from 1. Okay. This is xn, then times the sync function. Sync function, I need a t minus kt over t. So it is a t minus k times t and over t. I have these, right? Am I good? Hopefully. Yeah. And figure 2. I just plot t and xr. Okay, let's see. I have a hole. No, I don't have a hole. Okay, it's fine. Okay, this is the figure 2, that is figure 1, you see? Oh, I have more point. This is a... Oh, my symbol is ended at here, you see? This is a symbol, the last symbol is here. So the result date is also reached here. Okay? This point, this symbol related to a point here. Then after that we do not have a symbol, so it tends to be 0. Okay, then we can take more symbols. If I have this capital N, right? I take more symbols. For example, I take 40 symbols. Then what will happen? Yeah, 40 symbols. We have this one. This is a restored signal. This is the original signal together with the symbols. We have more symbols, right? More symbols. Oh, total 3.5. Okay, anyway. So we have the restored signal. Got it? Yeah. And we can also try if we use different sample step. Now I use 0.08 as a step, right? This is the period Nyquist. This is a sample step smaller than the Nyquist step, so it is a good one. If I choose a larger one, for example, 1.2, 1.2. This is larger, right? Larger than the Nyquist sample. Then I use this one. We can see what will happen. Okay. Yeah, we have these. You see, we have these. This is totally different with the original signal. You see, the original signal we have more details, but now I use T is a little bit large, just a little bit larger than the Nyquist. Then the result, when you restore, you have a signal. It look like this. You lost a lot of details. I can still put those samples there. The samples. I also put the samples there. The samples are n times t and xn with I use a different as a diamond here. F5. Okay. Oh, this is sorry. Come on. Yeah, it's still like this. You have too much samples. I can just watch the window. I just watch the window. I don't need so many. I can have these more samples, but when I display it, I can put the access for x run from 0 to 3 and y from -5 to +5. Can use this, right? I put this one. By this one, we will see only this part. Only this part. Okay. Yeah, okay. We only see x run from 0 to 3. This is figure 1 and figure 2. Oh, figure 2, I got something wrong. Some arrow. Figure 2. Arrow in axis. Oh, we can't do that? Let me see. Yeah, that one is good, right? Why this one doesn't work? T, maybe just that D is a problem, right? But okay. But it's work. It's still something wrong. What's a mistake? Line 11. Line 11 getting wrong. On line 2, oh, I have, that is fine. So what is the error? Okay, try again. I don't know which one is which one, right? So run again. Okay, now I can see the arrows. Okay, arrows at Y limb. Values must be increasing and non-annoying. Okay. I'm increasing, right? Okay. Or why they changing the location? Sorry. It's 0 to 3 and it's why this is it's -5. Sorry, -5 to 5. -5. Okay. Why put 0, 5? -5. Okay, now it's fine. So both graph from 0 to 3 in the x-axis in the time run from 0 to 3, 0 to 3. Those circles are the samples, right? So we take sample from here, and when we restore, the restored signal, they still go across those sample values, you see. Yes, they still go across those sample values, but the curve is not as same as the original one. Actually, quite different. This one looks more regular, like period, just one period. And here you see you have some more details. So that is because that T. Now I use I go back. Let me go back. Go back T to where's the T? I have a place here. 0.01. If I just use 0.1, this is Nyquist value, right? Nyquist sample step. If I use this one, what will happen? Okay, so this one is almost good. Oh no, it's still not good. It's still not good. You see, use the Nyquist one is still not so good. Start from here, from this point, then it's going down. But the original one start from this 2 and going up to 3, then going down. And here is start from 2 going down to some negative value, then go up back to that second value, right? So they are still not same, but some part is same, like this part, the last these 3 peaks, these 3 peaks, they are same. Yeah, these 4 peaks, 5. Okay, so we check it backward. I have 1, 2, 3, 4, 5. I have 5 peaks are same, but then these peaks are different. Here's a small peak with a high peak, right? This is a restored one, and the original one should be symmetrically, right? So this part is different. This part is different, and then again we have something similar, both sides similar. Okay, here's a different. Right? So this example, if we just use the Nyquist sample step, the restored signal here is not exactly same as the original one. But if I use a T smaller than this, even if it is smaller a little bit, like a 0.99, okay, this is a smaller than the original one, right? What will happen? We run it. Oh, still different. Two. Or maybe we need more samples, I think. Okay, let me more samples. Because this sample is run from 0 to n. If I run from negative n to n, what will happen? Because the negative side I don't have samples. Now I have, and this is also run from negative n to n. Okay, then run it. Oh, something wrong. Sorry. On line 16. Line 16 is this one. Okay, so this one I need a plus n now. Plus n plus 1. Okay, the index power. Alright, yeah, this time they are good, but still not so good. You see this part, this one, these 2 peaks here, this is the original signal. These 2 peaks are almost same, but here they are some different, somehow different. But basically these 2 waveforms, they are quite close. They are quite close, right? Yeah. If we, this is 0.09. 0.99. If I just 0.9, so not so close to the Nyquist step. Okay, so this time it looks good, right? This time it looks good. It's better, right? It's better. Theoretically, we were supposed, if T is smaller than Nyquist sample step, and then these 2 sides, they were exactly same. But you take sample, you can only take finite samples. Like here I take sample I have only negative n to positive n, so these totally amount of samples are 2 times n, 2 times n plus 1 samples. But in the formula here, in this formula, we suppose the summation run from negative infinity to positive infinity. Oh, that's a different. Here you have infinite terms, and here when you do the calculation, you only have finite. You only have finite samples. We only have finite samples. When you do summation, you only have finite terms. Right? Here's I do summation. I do this summation only for k run from negative n to positive n. If we use a larger n, then we will have less error. And of course, if t is larger than the Nyquist sample step, is larger than that sample step, no matter how many terms when you have you choose, the result won't good. XR will not be XC. Alright. Okay, that's all for today, and see you next time. This is okay, I have to a little bit early. It's fine, alright? Okay, see you next time. Bye bye.